Okay, yeah, thanks a lot, Youngbeck, for the invitation. It's a great pleasure to visit you guys here. Yeah, so today I'll be talking about some new kinds of quantum criticality that can arise in mixed states of quantum systems. And in making a talk, I always struggle with coming up with good images, especially for title slides. So this time I took the easy way out and just asked AI to generate 2 images based on these 4 words. And this is what you get. And I was tempted to ask ChatGPT to generate the rest of the whole presentation, but maybe next time. Okay, great. So yeah, let's begin with something that's I think very dear to the hearts of especially condensed matter, quantum matter theorists, and that's long-range entangled matter. Right. So this is basically quantum matter that's very far from our everyday classical reality of product-like states, and hence one of the most interesting phases of matter. So one prime example of long-range entangled states are quantum critical states. These are states that can occur at phase transitions between different phases of matter, say between ferromagnets, paramagnets. And indeed, these are long-range entangled. They have quantum correlations at all length scales. Right. Another prime example of long-range entangled matter is topological order. So unlike more trivial phases of matter like ferromagnets, these have no local order parameter, and instead one needs more subtle notions to describe them. So for example, these topological order have quasi-particle-like excitations that are called anyons, which can be neither bosons nor fermions. And these have very interesting applications for things like topological quantum computing, for example. So due to all these interesting properties of long-range entangled phases, these states are highly sought after in real materials and experiments. And until very recently, trying to realize these interesting states tended to be exclusively in the domain of solid-state materials, right? We wanted to find real materials which realize either quantum criticality or topological order, spin liquids, etc. However, recently, as you all probably know, there's been a lot of exciting developments in the field of quantum simulation and quantum computing. So yeah, I think most of this audience is familiar with many of these different approaches toward realizing systems of artificial qubits that are highly controllable. You can realize unitary gates, you can do single-site measurements, and much more. So these highly controllable quantum platforms provide a relatively new context for realizing long-range entangled states. Now you can try to literally build up the long-range entangled state as if you're carrying out some instruction set with Lego building blocks, right? You start out from the product state, and you can literally try to apply gates to construct these interesting states in quantum matter. And indeed, there's been a lot of recent progress precisely realizing this program. So, for example, in systems of Rydberg atom arrays and superconducting qubits, people have successfully realized what look like topologically ordered phases of matter. Okay. However, one has to keep in mind that these are still open quantum systems, right? We still have to struggle against coupling to the environment, noise, decoherence. And so this really begs the question, how do we think of long-range entanglement in mixed states, right? These are, after all, mixed states being achieved in a realistic experiment, right? So how do we characterize long-range entanglement in mixed states? And how do we realize non-trivial instances of long-range entangled mixed states? So at first glance, this might seem quite difficult. The mixed states that we're most familiar with are thermal states, right? Like equilibrium Gibbs states of local Hamiltonians, right? And these typically do not have long-range quantum correlations. Usually finite temperature is just bad news for any non-trivial quantumness, right? And indeed, if you start out with a quantum critical system and you turn on finite temperature, then these long-range correlations I mentioned are now cut off by a thermal length scale, right? And similarly, regarding topological order, if you turn on finite temperature, then unless you're in 4 dimensions, at least so far, there is no finite temperature topological order. Okay. So it's clear that equilibrium Gibbs states may not be the best place to look. We really want to find a highly non-equilibrium setting to see any instances of non-trivial long-range entangled mixed states. Yes.
What's special about D equals 4?
Okay, that's a good question. So here, I guess I have in mind specifically a Tor code model of topological order in which, in 4 dimensions, you can have basically instead of point-like anion excitations, you can have loop-like excitations only, right? And it turns out at finite temperature, it's much harder to proliferate these loop-like excitations. So the topological order is stable. Yeah. Okay, so it's clear that we need some highly non-equilibrium setting to get any non-trivial mixed states. And so we want to consider a setting of highly controllable open quantum systems. So quantum systems in which the coupling to the environment doesn't lead to trivial thermalization, but now you can control the interface with the environment very carefully in different ways. Okay. And as usual, we can draw inspiration from quantum error correction and fault tolerance, because there for decades, they've been considering a very closely related problem of how do you stabilize quantum information coherently in a noisy environment, right? This is basically hand in hand with this question of stabilizing long-range entanglement in an open quantum system. Okay. So there, the approach for fault tolerance is usually active error correction. So in active error correction, you basically carry out measurements to have a best guess of where the errors occurred. And then based on the measurement outcomes, you apply some feedback, you apply some corrective unitaries to correct those errors. Okay. So this is the basic spirit of active error correction. You apply measurements, get some knowledge of the errors, and then you apply feedback based on the measurement outcomes to correct them. Okay. And fault tolerance might still be several years away. However, it's one of the holy grails for quantum computing, right? So many of these quantum hardware platforms already have or are developing the capability to do what's called these mid-circuit measurements. So measurements along with unitaries that you don't just do at the end of a protocol, you can do them dynamically. Okay. So many of these quantum hardwares already have this mid-circuit measurement capability. And so this begs the question, even before we reach full-fledged fault-tolerant quantum computing, can we use these type of operations in some interesting way to realize some interesting mixed states? Okay. So this will be one of the motivations for the first part of this talk. So this is work in progress with a postdoc at Perimeter, Peter, Sagar Vijay, who's a faculty member at Santa Barbara, and his student Hsieh Zhang. So in this first part of the talk, we will use precisely this type of operation of measurements followed by feedback to efficiently convert simple pure states into non-trivial long-range ordered or even critical mixed states. Okay, so one example I'll present is some protocols for converting symmetry-protected topological states or SPT states into GHZ or topological order via measurement and feedback. I'll probably focus on this GHZ order more in the interest of time. And furthermore, I'll try to show some examples in which we can also use measurement and feedback to convert simple free fermion states, such as a Chern insulator, into critical spin systems. So mixed states of spin systems with algebraically decaying correlation functions. Okay. And in the second part, I'll talk about a somewhat different approach for realizing interesting quantum critical behavior in mixed states. Now, instead of starting out with simple pure states, I'll start out with already non-trivial pure states, so quantum critical pure states. And then basically we were interested in asking how does such long-range entanglement in pure states survive under local decoherence, under some simple noise channels? Does the local decoherence just kill the long-range entanglement? Does it preserve it? Does it alter it in an interesting way? And as you'll see, there'll be concrete examples of all of the above options. Okay. So using this different route, we'll also be able to achieve some critical mixed states. So more specifically, I'll show you that we can define in a precise sense renormalization group flows or RG flows between different quantum channels. And these RG flows will actually determine the entanglement structure of the resulting mixed states. One question we're very interested in is how quantum are these resulting mixed states? And these RG flows will help us answer that question. And I should point out that there was a related work from Zhangyan and Senke at Santa Barbara and Chaming at Cornell, in which they consider a related question of decohered quantum criticality, although they focused on very different aspects of the problem. So I encourage you to also check out that reference. Okay, so let's jump right into the first part. So again, just to remind you, in the first part, we want to consider this type of operation that I'll call local adaptive quantum circuit. So a local adaptive circuit consists of both local unitary gates, local measurements, and most importantly, the ability to process the measurement outcomes and decide what to do later at a later time step in the circuit. Okay. So hence the name adaptive. Based on the measurement outcomes, you can decide what unitaries, what measurements to apply later in time. Okay. And the motivation for why we and many other people consider such local adaptive circuits is because they allow you to shortcut the preparation of long-range entangled states. Right. So if you have a quantum circuit that consists of purely local unitary gates, then there's a Lieb-Robinson bound which restricts how quickly that local unitary circuit can establish long-range correlation. Right. So it turns out that with a local unitary circuit, you need depth or time of order system size to prepare any long-range entangled state, like a quantum critical point or topological order. However, the Lieb-Robinson bound assumes, local unitary evolution, right? And so with local measurements and non-local classical communication, basically the ability to take all this classical data and decide what to do at a future time slice, this setting is beyond Lieb-Robinson. And this is why local adaptive circuits are actually able to prepare long-range entangled states like topological order in order 1 time that's independent of the system size. Okay?
Sorry.
Yeah.
So, what's the consequence of the local measurement here? So aren't you unentangled after you do the local measurement?
Yeah, that's right. That's a good question. So yeah, so I didn't mention that this shaded dots in the background are meant to indicate ancilla qubits. Okay, so we'll allow coupling to ancilla degrees of freedom. We want basically an order 1 overhead of ancilla, so like maybe 1 or 2 per physical degree of freedom. So we're allowed to bring in those ancillas, couple them with unitaries, measure the ancillas, etc. Yeah. So now you can have a non-trivial state remaining if you're just measuring ancillas, right? Yeah, thanks for the question. So in all these previous works, all these groups started out with short-range entangled pure states, like say a trivial product state, and arrived at long-range entangled pure states. Okay, and this is pretty fine-tuned. So here, basically, we started with some ideal fixed point state with 0 correlation length, and due to that, that restrictive structure, we arrive at a particular pure state that's long-range entangled. So all these local measurements are producing a bunch of trajectories of pure states, and the feedback, the corrective unitaries are able to converge all those measurement trajectories back into a single target pure state that's albeit long-range entangled. Okay, so we go from pure state to pure state, but this is kind of a very fine-tuned setting. And so in general, this local adaptive circuit will convert pure state to mixed state. And so we would like a more general formalism to describe this behavior. Okay. So this is the slightly more general picture of what we like to consider. So again, we start out with a pure state psi naught that's defined on a system with, say, 2 types of degrees of freedom, A and B. these can be, as you'll see, this can be both, sublattice degrees of freedom or spin and charge. It can be some extensive partitioning of your system. Okay, and so as before, we'll perform local measurements on the A degrees of freedom, and then we'll feed the measurement outcomes into some simple classical processing to decide what to do later on the B degrees of freedom. So what unitaries to apply on the B degrees of freedom. Okay, and we want to consider this as a quantum channel that converts the pure state Psi0 into the state supported on the B degrees of freedom, which will in general be a mixed state. So we're not interested in what happens to the A after all this, because the A's are measured out and typically trivial. Okay, so we want to view this as a quantum channel from Psi0 to the reduced density matrix on B, rho B. And it turns out that we can think of rho B as basically tracing out A after applying a big unitary on Psi0. And this big unitary on Psi0 is some control unitary. Okay, so it's basically a control unitary described by projection, like sum over all outcomes of the projection operator onto the outcome, followed by the feedback you perform on B, depending on that outcome. Okay, so yeah, so it's basically this rho B has a, oh, sorry, yeah, I've got a little bit ahead of myself. So yeah, okay, so yeah, I want you to think of rho B as arising from doing a control unitary on the whole state and then tracing out A. Okay. So on general grounds, to convert from short range to long range entanglement, this control unitary cannot be a local finite depth circuit, right? Precisely for the reason I mentioned earlier, that for local finite depth circuit, there's a Lieb-Robinson bound that limits the generation of long range correlation. Okay, so this control unitary will not be simple. It will not be local finite depth. However, the key is that we're kind of absorbing all the complexity into local quantum operations, these local measurements, local unitaries, but we have this non-local classical communication. So we have the ability to use all the classical data everywhere to decide what to do locally. Okay, so all the complexity is absorbed into this non-local classicality. And this is, again, kind of experimentally motivated, right? Because the quantum operations are the hard part. The classical processing, we like to think, is the easy part of quantum computing. Okay, so right, so again, just to emphasize, we like to view this channel as going from Psi0 to rho B. However, it will be useful to think of the purification of rho B, which is just this control unitary applied to the full system. Okay, so this U Psi0 is precisely a purification for rho B. Okay. And the parent Hamiltonian for this purification is just given by conjugating the parent Hamiltonian of the original pure state by this control unitary. Okay.
So is the entire process unitary?
No. So we've done right. So we've done measurement and feedback. So the entire process is not unitary. However, we can think of rho B as coming from a pure state that's obtained by applying a unitary to the original pure state. Okay. So we perform local measurements and feedback, which ultimately will result in a mixed state on both A and B. Right. So we go from physically we go from a pure state on the entire system to a mixed state on the entire system, which cannot be unitary. However, I'm saying we're only interested in the channel from the pure state to rho B, to the reduced density matrix on B. Okay. And I'm saying that rho B has a purification, has a natural purification that's just purified by A. And that purification comes from applying a unitary to the pure state. So in other words, it can be equally well carried out by a big control unitary on the original pure state, and then tracing out A. Yeah. Usually complex, right. Like to carry out that unitary is probably pretty hard, and so this measurement and feedback is like a natural way to shortcut that, right. Yeah.
But isn't it the case that controlled unitaries are very difficult to realize experimentally?
Yeah. Sure. Yeah. We're not saying we want to realize this, right? This is a theoretical way to think about the physical process of measurement and feedback. Okay. Yeah. Okay. Yeah. Thanks. So more specifically, we want to convert some type of hidden or non-local order in this initial pure state into some genuine long-range order in the resulting mixed state on B by doing this type of measurement and feedback. And I'll show you a concrete example very shortly. So in this framework, all we rely on is some hidden order in the initial pure state. If it's there, then we're guaranteed to have a long-range order in the mixed state. And hence this convertibility to long-range order is really a property of an entire phase of the initial state. It's a pretty robust property of the initial state. And there were some related works from Santa Barbara, Harvard, and so in these works, they consider a similar setup of measurement followed by classical post-processing. Okay. But in general, there can be some overlap between classical post-processing and unitary feedback, but one doesn't necessarily include the other, right? Like, for example, many types of classical post-processing cannot be realized by simple local unitary feedback. And also the examples we will consider will be very different than in these papers. Okay, so let's just begin with an explicit toy model. Okay, so we want to consider a 1D system of qubits with two sublattices A and B. And we want to consider a 1D cluster state, symmetry protected topological state. So specifically, we want to consider the ground state of this interacting Hamiltonian consisting of interactions of ZXZ for every 3 neighboring qubits. Okay. So this is the ground state of this Hamiltonian is a non-trivial SPT protected by 2 global symmetries, 2 Ising symmetries on each sublattice, on A and on B. One way to see why this is a non-trivial SPT state is to look at a string order parameter. So if one considers an operator in which Z's are applied at the endpoints on the B sublattice, and then you also multiply by all the X's on the A sublattice in between, this constitutes a string order parameter. And one can easily check that the ground state of this Hamiltonian has string order parameter 1. Okay. Basically, this is a completely commuting model. So all these operators take value 1 in the ground state. So you can multiply them head to tail. The Z's in the middle cancel out. So you end up with this type of string operator that's takes value 1. Okay, so this is one way to see why this is a non-trivial SPT. So this is the pure state we begin with hidden order. And now we want to convert this into genuine long-range order. Okay. And yeah, so far this is not our work at all. This dates all the way back to Briegel and Rasendorf in very early days. So there's a simple way to convert this into genuine long-range order on B. And basically we want to turn this string of X operators into numbers, right? We just want to convert those operators into numbers, and then this string will just become the endpoint, the 2-point operator that we want. Okay, so basically what we do is we measure all the A sites in the X direction. So now we get some number like plus or minus 1 for the middle of the string. And then now we want to get rid of that ambiguity of plus or minus 1 by doing unitary feedback, right? So more physically, measuring X on the A sites tells you about the domain wall information for neighboring B sites. Okay. So by measuring X, you know about the relative Z orientation for B sites far apart. So more specifically, we take all that measurement outcome for the X measurements, and then based on that, we decide whether or not we need to flip a given qubit on the B site or not. So the goal is to get some long-range ZZ ferromagnetic order. Okay. Yeah. So concretely, we apply this this unitary feedback, which again is simple quantumly. It's just a single qubit flip, but it depends non-locally. It depends on all the measurement information coming from these X measurements. Okay. So we do measurement and feedback, and you can easily convince yourself that at the end of the day, we get a pure GHZ state, all up plus all down on the B system after measurement. Okay. So again, here it's a very restrictive setting. We started with a fixed point, zero correlation length state, and measurement and feedback converts it into a single pure GHZ state with long range order. Okay. Yes.
Hi, I'm confused about what the initial state is.
Sorry, yeah. The initial state is the ground state of this SPT Hamiltonian. So it's a non-trivial SPT state with this hidden order. Okay.
Can you give me a concise description? It's just like, does it mean that locally X is correlating with Z or something? Or like
Yeah, thanks. So we're dealing with the ground state of this Hamiltonian. All these operators in the Hamiltonian commute. So the ground state is completely specified by fixing all these ZXZs to be 1. It's what's called the stabilizer state, in which all these stabilizers take value 1. So indeed, all the X operators on B is completely correlated with the ZZ nearby, right? Yeah. Thanks. Yes. Yeah.
So this reminded me of the fusion gate node. You have two entangled states, you make two qubits go to a fusion down, you have a long chain of entangled states from two smaller entangled states. Is something similar going on here?
Sorry, I'm not sure I understood the fusion. What operation is?
Fusion gate helps you to like create longer chains of entangled states. Let's say if we have like n qubit entangled state on one side and qubit on the other. You measure two qubits, now we have 2n minus 1.
Right.
Qubit entangled state.
Yeah, I think eventually all these can be probably related to each other, because whether or not you're measuring single qubit or 2 qubit for fusion depends on whether or not you want to apply a unitary before the measurement or not. You can probably convert single qubit into 2 qubit measurements by applying some simple unitary. So I think they're all related. Yeah.
Yeah, so like the initial ground state of the SPT, does it also have a long range correlation?
No. Okay. Yeah. Thanks for the good point. So again, the rules of the game here is we want to start with a simple pure state that can be prepared with a finite depth circuit. And indeed, this hidden string order is not an obstruction to preparing it with a short depth circuit. So indeed, preparing the cluster state is easy. You just apply some control phase gates on a product state, like one layer of control phase gates. So it's easy to prepare. And then this pretty simple measurement and feedback can convert it into genuine long range order. Yeah. Okay. Yeah. Thanks. Right. So the point I want to make is that this again is the ideal setting of pure state to pure state, because we're dealing with a fixed point state. So now we want to consider the more general setting of what if you perturb away from this fixed point state, right? So we can add to the ideal cluster state Hamiltonian some perturbations, basically some additional interactions, which now result in finite correlation length. And so these additional interactions, we choose to preserve the two Ising symmetries I described before. So they preserve the symmetries that are protecting the SPT state, and thus the SPT phase survives up to a certain strength of that perturbation, after which it transitions into some symmetry breaking type state. Okay, so we perturb the ideal cluster state, and now we still get non-trivial SPT states. However, away from this fixed point limit, the string order no longer is a perfect 1 value. It would be some order 1 number that's still finite. Okay. And it's easy to check that after this exact same measurement and unitary feedback I described on the previous slide, what's left over on the B sublattice is a mixed state in which the ZZ correlations precisely take the same value as the string order of the initial pure state. Okay, so there's this same type of measurement feedback will just kill this the bulk of the string and leave you with the 2-point function. Okay, so just to summarize, after measurement and feedback, we get this long-range GHZ order on the B subsystem. And once the SBT transitions into a different state, the string order will disappear. And so this long-range order of the mixed state will also disappear. So this mixed state will undergo some transition precisely when the initial pure state undergoes the transition. Okay, so this mixed state on the B sublattice with long-range ZZ correlation is somewhat unusual because it's a long-range order that's coexisting with extensive entropy. This mixed state on the B system is basically, in the purification picture, it's extensively entangled with the A sites. So it has extensive entropy. So this is clearly a rather, a manifestly non-equilibrium state in 1D, right? At finite temperature, for example, you cannot have long-range order, right? Sorry. Right, okay, but however, the ZZ correlation by itself is not really a true testament of quantumness, right? You can have purely classical ensembles with long-range ZZ correlation, right? So how quantum is this mixed state on the B system? So one pretty small theorem that we can prove is the following. If we have a mixed state in which the 2-point ZZ function is long range, it's constant as you take I and J apart, and if there's an Ising symmetry intact for this mixed state, then this mixed state cannot be simple in this sense. This mixed state cannot be an ensemble of short-range entangled states, where short-range entangled states are defined by any state that you can prepare with a finite depth circuit acting on a product state. Okay, so the takeaway is that this long-range ZZ correlation, in conjunction with a global Ising symmetry that anti-commutes with the local operators, guarantees that this mixed state is quantumly non-trivial in this precise sense. Okay. All right, so that's a description of that's some intuition for what this mixed state in this part of the phase diagram is. And now we want to go to this interesting critical point, right? Because as I said, when the initial pure state becomes critical, this mixed state will also become critical. But how quantum is this critical mixed state, right? So we can analyze this mixed state at the critical point in a fair amount of detail. We can calculate correlation functions for ZZ operators. And it turns out it has the same power law decay as for a pure state Ising conformal field theory. We can also calculate string orders, what's called disorder parameters. We can find the power laws, and we find that actually has twice the power law decay for Ising conformal field theory. And more interestingly, we can compute entanglement measures for this mixed state. Right. So here we have this critical mixed state rho B. We can partition it into an interval of size x and its complement, and we can ask about the entanglement between this interval and its complement. Right. So as you may know, for a mixed state, the usual entanglement entropy is no longer a good measure of quantum correlations across this partition, because this mixed state is now entangled with some environment, right? And so the regular entanglement entropy mixes together all those correlations. So we would like a measure that's sensitive to only quantum correlations across this partition. And it turns out that the entanglement negativity across this partition does capture only the quantum correlations. So I won't define it right now, just to avoid being too technical, but you can think of it as a measure of quantum correlations for a mixed state. And what we find is that this negativity for this mixed state at criticality has this log scaling with the size of the interval. And so it has this universal scaling form that's very typical of conformal field theories. Okay, you might know that for a pure ground state that describes a conformal field theory, the entanglement entropy also has this log scaling, and the prefactor of that log is proportional to the central charge of the conformal field theory. So here we find that for this critical mixed state, the negativity also has the same type of log scaling, but now with a different coefficient. So we get this data just from simple exact diagonalization of this model. And here are the data points corresponding to this critical mixed state. And by comparison, here is the negativity for a pure state of a critical Ising model. So as you can see, the slope is lower than that of the pure state CFT. And that's pretty natural from the point of view of monogamy of entanglement, right? So for this mixed state, some of the degrees of freedom are now coupled to the environment. So they're less able to participate in long-range entanglement within the system. And so this is a somewhat intuitive way to understand why the slope is lower than that of a pure CFT. Okay, and once again, this log scaling of negativity is a direct signature of the non-equilibrium nature of the state. Some of you might know that for a Gibbs state or equilibrium Gibbs state of a local Hamiltonian, such states have a strict area law for entanglement negativity. This is proven, I think, in an appendix in this paper. So the fact that we're getting a log scaling is a direct signature that it's not it looks nothing like a Gibbs state of a local Hamiltonian. Okay.
Is this quantity related to this partial transpose?
Yeah, so the negativity is defined by doing a partial transpose operation on a subsystem. Yeah, I think I have a more explicit formula later that will show that. Yeah. Okay, so that's a simple toy example of how measurement and feedback can give you interesting mixed states of long range or critical entanglement. Yeah. Yeah.
So you showed that there was a mapping between the short range all the way collapse field also the long range.
Mm-hmm.
Because there is a digging time that actually underlies the. Is it obvious that when you destroy the short range also processing the long range picture, it's the same value?
Oh, yeah. I didn't explicitly show that calculation, but yeah, it's pretty straightforward. Basically, this whole measurement and feedback just kills the middle of the string. I can show you more details later, right? Yeah, but yeah, it's a exact calculation. There's no ambiguity. It's literally the same value as the original string order. Yeah. Yes. Oh, this constant here. Oh, that. No, yeah. Here it's non-universal. It's just some. Oh, that's true. Yeah. Right. Right. Yeah, I'm not sure. I have to think about it. It's a good point. Yeah. Right. Okay. So yeah, so that's a very simple example, and one can consider even more non-trivial examples that are motivated by the physics of fermion systems and Grueseler projection. Right. So in condensed matter, there's a pretty famous construction that's called a Grueseler projection, in which you start out with a free fermion system, free fermions with both spin up and spin down, and then you project that wave function onto an effective spin wave function by enforcing that the total occupation per site is 1. Okay, so you can think of basically the Grueseler projection as doing a forced measurement on a free fermion system in which you enforce that you get measurement outcome 1 for total occupation number per site. So this gives you a spin wave function, and this type of spin wave functions can be very interesting. Grueseler projection can give you interesting like critical spin systems, topologically ordered spin systems, etc. A whole zoo. And so motivated by that, we want to ask, what if you start out with free fermion systems, but now you do measurement that's not force measurement, right? We want this to be physical, achievable in a lab, right? So we can't guarantee measurement outcome, like occupation number 1 per site. We'll get some random numbers like 0, 1, or 2. However, by doing feedback, we can kind of mitigate this randomness a bit and still get some interesting spin physics arising from it. Okay, so that motivates this next set of protocols. Yeah, so let me skip the 1D example in the interest of time, and just go to the more interesting 2D case. So in this example, I'll show how we can convert an initially gapped pure state with exponentially decaying correlations into a critical mixed state. Okay, so the starting point is a churn insulator in 2 dimensions. This is basically a analog of an integer quantum Hall effect. It's a insulator in which there's a chiral edge mode at the boundary, if the churn number is 1. And so it's a ground state of a gapped Hamiltonian. It has exponentially decaying correlation functions. However, if one considers a composite operator that's obtained by dressing a local fermion operator by some eta operator, in which eta is some phase factor that depends on the occupation number everywhere else in the system, weighted by the relative angle between those positions and the original position, then this dressed operator actually has some interesting power law decay in the churn insulator state. Okay, so basically this composite operator that's effectively non-local has a power law decay in the churn insulator. Okay. So this is kind of mysterious, but it's just the physics of flux attachment. Okay, so the cleanest way to see this is to start out with just consider the Laughlin wave function. So Laughlin wave function for the lowest lambda level integer quantum Hall effect. So this Laughlin wave function is given as follows. And basically this type of dressing we're doing is just factoring out a phase factor of the Laughlin wave function that again depends on the relative position of all the particles, right? And so this phase factor that we're extracting from the Laughlin wave function is nothing but the first quantized version of this eta operator. Okay, so after factoring out this phase, we get a transformed wave function that's now describing a system of bosons. Okay, and the system of bosons, one can check, has precisely this type of power law decay. In this case, with power law 1/2. Okay, so yeah, so all this phase factor is doing is basically attaching a statistical flux that depends on the positions of all the particles everywhere. Yeah. Sorry, what? Yeah, psi tilde is a bosonic wave function.
But the operator, the one on top.
This one is a fermionic wave function because when you interchange 2 particles, you get minus sign.
And C, the one C tilde.
C tilde.
The
What C? Oh, C. C dagger. Oh, C tilde dagger.
Yeah.
Well, yeah, okay, that's a good point. It's probably a bosonic operator. It should be, yeah. To be honest, I haven't checked the explicit computation myself, but it has to be. It's based on this picture.
It shows the coefficient such a way that the photo remark.
Right, yes, yeah.
It looks like one of those Jordan Weber transformation.
Yeah, it's or 2D bosonization, pretty much. Yeah, that's right. Mm-hmm. Okay, so the takeaway is just that the churn insulator also has this type of hidden order that depends non-locally on the occupation number on all sides. Okay, so now we want to again leverage this into some interesting measurement and feedback protocol. So the setup is as follows. We want to start out with a churn number 1 state for spin up electrons, a churn number -1 state for spin down electrons. And now we want to measure the total occupation number on every site. So on both systems, just the total occupation number per site. So after that, we'll get some string of outcomes for all the sites. And based on that data, we'll apply some unitary feedback. That's just, okay, so sorry, after performing these measurements, we get an effective spin system for the whole system. And we can perform some unitary feedback. That's just some phase rotation, some single qubit phase rotation, whose phase factor depends on all those measurement outcomes in precisely the sense I described before. So it's just the sum of all occupation numbers weighted by the relative angle. Okay, so the essential physics is we're using the feedback to kind of build in this eta operator. We're building in this non-trivial phase factor into the spin system. Okay, so more concretely, we can consider spin operators. For example, S plus is just C dagger up, C down. And after applying this unitary feedback, this just attaches one of these phase factors to the operator. And similarly for the S minus operator. Okay. And so again, a fairly straightforward calculation shows that after this measurement and feedback, you get a mixed state that's effectively defined on a spin system, which has this power law decay that originates from this non-local order of the Chern insulator. Okay. So yeah, so this is a pretty interesting example where we started out with a gapped pure state, and again with purely local quantum operations but non-local classical communication, you can get a critical mixed state. Okay, and it's still an open question to understand the entanglement properties of this resulting mixed state. We like to examine that more. All right, so I see I'm running pretty low on time. I'll try to be brief with the second part. So again, the starting point of the second part is very different. Now we want to start out with a pure quantum critical state and see what local noise does to it. Okay, and this is part of a bigger program of examining how long-range entanglement fares under decoherence, right? And for example, there has been a very nice recent work from Harvard and Berkeley group in which they look at toric code under local decoherence, and they find interesting connections to the property of the mixed state, like the entanglement negativity, etc. Okay, so here's the setup for the second part of the talk. Again, we're considering effect of quantum channel on a pure state. So again, quantum channel is the general operation that maps mixed states to mixed states. And here we're dealing with a explicitly local quantum channel, not like the first part of the talk. Right, so here the local quantum channel will literally be a tensor product of single qubit channels. And we'll focus, in fact, on dephasing quantum channels. So these quantum channels are defined by either measuring the qubit in a given direction V with some probability P, or doing nothing. Okay, that's what the dephasing channel does. It would be convenient to define what's called a dual channel N star. And this is basically, you can think of it as the Heisenberg picture for channels. Okay, so the original channel N acts on the state rho, right? But the dual channel acts on operators, and it's just defined to reproduce all the right expectation values, just like the usual Heisenberg picture. Okay, so for example, say you want to apply a dephasing in the z direction with some strength p. One can check that the dual channel maps the Pauli operators to these. So it just suppresses the x and y Pauli operators by a factor 1 minus p, and it keeps the z operator unchanged. Okay, so now we want to apply this type of simple local quantum channel to an interesting critical pure state described by a conformal field theory. Okay, and we want to look at the properties of this resulting mixed state. So one thing we can say is that we can map these channels N into boundary conditions of several copies of this conformal field theory. Okay, so let me give you a taste of that, of why that's true. So say you want to compute some property of the mixed state rho, like say a Renyi entropy of a subsystem for rho. So this is defined by just log trace reduced density matrix to the power n. So for this, we can use standard techniques. So we can write this trace rho to the n as just expectation value of a permutation operator of n replicas in n copies of the state rho. Okay. So some of you might be familiar with a Renyi-2 calculation in which the permutation operator reduces to a swap operator, right? Okay, so now we can we just plug in rho being a channel applied to the state, and now we can move the action of the channel onto a dual action acting on the permutation operator. So now we get the expectation value of some operator B that's defined by the dual channel acting on the permutation operator, and the expectation value taken in the original, in n copies of the original critical state. Okay. And finally, we can map operators into states on the double Hilbert space. And so this whole thing reduces to some wave function overlap of effectively 2n copies of the conformal field theory on one part of the overlap, and this operator state B on the other end. So the picture for this calculation now looks like 2n copies of the CFT overlap with this boundary condition, which depends on the channel n that was applied. Okay, so this is how channels turn into boundary conditions for CFT. Okay, and this applies to all sorts of entanglement measures you're interested in. For example, again, we might be interested in entanglement negativity. It's a good mixed state measure. And entanglement negativity is defined by taking a partial transpose of the density matrix on the A subsystem and then taking the nth power. And all this maps to some generalized boundary conditions. Okay, so again, we have very similar pictures of several copies of the CFT overlap with some boundary condition depending on the quantum channel that was applied. Okay, so now this is the upshot is that to ask, what are the properties of this resulting mixed state? Now that maps into the question of what do these boundary conditions flow to in the IR limit of the CFT, right? What conformal boundary conditions do these all flow to, right? So that's how we can define an RG flow for quantum channels. So let me be more concrete about this. So let's start out with a simplest thing to ask for this mixed state rho. Just what's the entropy of rho? More specifically, what's the second Renyi entropy of the entire rho state? Okay, so no partition or anything, just what's the entropy of it? So that's just negative log trace rho squared. And so what we find is that there's a extensive part of the entropy that just scales with the system size. This is natural because every qubit is being dephased a little bit, right? And the more interesting thing is this universal subleading part, this log G, which depends on the channel that was applied. And this log G is nothing but what's called a Affleck-Ludwig boundary entropy in the conformal field theory. Okay, so I don't want to go into too much detail. Let me just point out that this G function plays a similar role for understanding the RG flow of the boundary as the central charge C does for the bulk RG flow of the conformal field theory. Okay, and more precisely, it dictates which channels can flow under RG to which other channels. So a channel with larger G can flow to a channel with smaller G, but not vice versa. Okay. And sorry, I should probably clarify what I mean by flow. So by flow, we're basically looking at the long distance or IR limit of the system and looking at the universal properties in that limit. Okay. Okay, so let's see what happens for one of the simplest critical states. That's just the critical transitionalizing model in 1D. Okay, so we're interested in the ground state of this 1D spin chain model. And we've chosen a convention where the interaction is XX and the local field is Z. So what we find is the following RG flows for quantum channels. So yeah, let me explain this in detail. So here, if we consider applying dephasing in the Z direction, we find that it corresponds to a marginal perturbation, and this leads to a continuous set of fixed points. Okay, so what this means is that for every strength of the phasing in the z direction, we get a different fixed point of the conformal boundary condition. Okay, so the phasing in the z direction always gives log g equals 0, and it gives you this continuous family. On the other hand, dephasing in the x direction is a relevant perturbation. It has log g equals minus log 2. And that means if you do a arbitrarily small amount of dephasing in the x direction, then you'll flow to complete dephasing in the x direction. Okay, that's what the idea of relevant perturbation means. And finally, if you consider dephasing in the zx plane, we find that that's even more relevant as log g equals minus 2 log 2. And so all these channels, when weakly perturbed in this direction, will end up flowing toward that. Okay, so we obtain this type of RG flow diagram by just numerically computing this g function for different system sizes. And we can see that for bigger and bigger system size, they flow to a particular value, like in this case, minus 2 log 2. Okay. Okay, so these are some of the RG flows for dephasing channels applied to this criticalizing ground state. So yeah, let me skip this in the interest of time too. Basically, with these CFT techniques, we can compute many quantities of interest. We can compute mutual information between intervals, that are both A and its complement or two disjoint intervals. We can compute a lot of stuff. However, to me, the most interesting thing is, again, the integument negativity results, because again, this is like a measure of how quantum are the resulting mixed states one gets, right? And so let me show you the results here. So just to remind you, we're partitioning the mixed state into A and A bar and computing the integument negativity between A and A bar, the amount of quantum correlation between A and A bar. So when we apply the dephasing in the x direction, recall that the RG flow indicated that was a relevant perturbation, right? And that a small amount of x dephasing should flow to complete dephasing. And complete dephasing gives you a completely classical state, right? And the completely classical state has 0 negativity. And indeed, that's consistent with what we find for the integument negativity of this x dephase state. You can see that, okay, so here's the original critical pure state with log scaling of negativity. But even for a very small strength of dephasing in the x direction, this log scaling becomes area law pretty much immediately. Right, so this is consistent with the fact that this is a relevant perturbation that immediately in the IR flows to a completely classical state. Okay, and this is somewhat counterintuitive because for finite p, like 0.1 or 0.2, the resulting mixed states actually they still have power law decaying ZZ and XX correlation functions. So based on correlation functions alone, they would appear quantum, right? And yet this more precise negativity calculation shows that they're actually classical in the IR limit. Okay, so yeah, we still need to wrap our head around this, but I just want to point out it's somewhat counterintuitive.
When you say the resultant state, you mean the fixed point state in the long time of the dynamic state?
Well, okay, so sorry. So the dynamics here is just a single shot dynamics. We're just applying one layer of quantum channel with strength P to a given critical pure state. Yeah, so the RG flow, I mean, is like an RG flow for making the space direction very big. Okay, we're interested in the properties for large L, right? Yeah. Okay, and now we can consider the z dephasing. So just to remind you, the RG flow in the previous slide indicated that it was a marginal perturbation. And indeed, again, that's consistent with what we find with integument negativity. So here are the negativities for different strengths of P dephasing in the z direction. And you can see that the slope changes continuously with P. Again, consistent with the idea that you have a continuous family of fixed points. Okay. The dephasing in the y direction also turns out to be quite interesting. Here we find that at least for P below some threshold value of around 0.6 or 0.7, the Y dephasing turns out to be irrelevant. And what this means in terms of negativity is that if you look at the log scaling of negativity, even the slope of that log scaling doesn't change. Okay, the slope of the log scaling is the same as the original pure state CFT. So this is again somewhat counterintuitive. Basically, the Y dephasing for P less than 0.6 flows back to the original pure state properties. Okay. Okay, so that's pretty much all the results I want to present. Let me just conclude with some open questions that we're interested in. Obviously, experiments would be nice for all of these setups, right? And indeed, these mid-circuit measurements, these adaptive circuits are quite realistic. So in fact, we recently collaborated with Quantinuum, which is one of the trapped ion quantum computing groups, and also Isaac Kim at Davis and his student Arkan Tiku, to basically carry out some simple adaptive circuit to prepare a toric code state. Okay, so these adaptive circuits are very realistic in several platforms. This occupation number measurements are pretty realistic for optical lattices. It'd be interesting to carry out these Gutzwiller motivated protocols I mentioned there. And finally, for the second part, a lot of these entropies, negativities can be probed with these fairly recent shadow topography methods on quantum simulators. Conceptually, it'd be interesting to further understand the constraints for local adaptive protocols, right? So they can beat local unitary circuits, they're more efficient, but they can't do everything, right? So exactly what can or cannot they do? We'd like to understand that in more detail. And finally, this is related to the last question. So I showed you basically single shot type dynamics, like just one layer of operations. But it would be interesting to consider local adaptive dynamics in which you're iterating measurement and feedback over and over. And indeed, there have been some recent works considering measurement and feedback, but with local feedback, right? With local feedback in which the operations you apply depend only on the measurements that are performed before but near that site. Okay. And in those cases, they found that the resulting, you can get some mixed state transitions, but those are classical in many sense. Like you wouldn't expect like log scaling of negativity, for example. And so this type of non-local feedback in the first part of the talk, I think is really essential to being able to stabilize long-range entanglement in the mixed state. But we still need to think about what interesting dynamical protocols there are. Okay, so let me just conclude with a summary slide. So in the first part, I showed you how measurement feedback gives rise to non-local quantum channels that convert simple pure states into long-range or critical mixed states. And one interesting example is starting out with a gapped pure state, Chern insulator, getting a critical mixed state on the resulting spin system. And in the second part, we understood the effects of local noise on quantum critical points. We mapped channels to boundary conditions of CFT, which allow us to compute RG flows for these channels, and these help us understand the entanglement structure of the resulting mixed states. Okay, so I hope I've convinced you that noise, mixing things up, is not always a bad thing and can actually enrich the physics. So thanks for your attention.